Thank you all for coming today. Today we have a very special treat, and everyone knows Dr. Dale Purves. And how I got to know Dr. Purves was through my dissertation work, where he worked on dispersal ganglion back in the 60s, 70s, and 80s. And that really, every time I cited his paper and I looked at his work and how it affected me, I finally got the guts to actually talk to him this last year or so. And that's why he's here today. And this is the first time I had to introduce somebody where I had to actually truncate it down to a page because it just keeps going. But just a little background about Dr. Purves is he graduated from Yale University, summa cum laude. He had received his MD from Harvard Medical School. And after that, he was an intern in surgery at Mass General and did a stint in the Peace Corps in Venezuela, and did surgical residencies in Mass General Hospital. And then he found out that he liked research. So then he moved on and did a postdoctoral fellow at Harvard Medical School as well as University College London. And after that, he rose through the ranks at Washington University in the Department of Physiology and Biophysics, from assistant to full professor. I think one of the most notable things about Dr. Purves is that he is a National Academy of Science member. He is also a Jacob Javits Neuroscience Investigator twice. I want to reiterate that in the period of span of 6 or 7 years, he got his first Jacob Javits, and then he got the second one. I've known a lot of people who've gotten one Jacob Javits, but not two. He's also a Alexander Forbes Lectureship from the Grass Foundation, which is a really prominent foundation honor, as well as used to editor-in-chief of J Neuroscience from 88 to 93. And Dr. Purves has over 100 publications, over 16 books that he signed today, and several book chapters and review articles. So I personally think that Dr. Purves really shaped how we look at the central nervous system. And now, in the last 10 or 15 years, he has really reshaped how we looked at cognition and visual and auditory function. So without further ado, Dr. Dale Purves.
Everybody hear me okay? Is that working? Kevin, thanks a lot. Thanks especially for the invitation, but thanks for your introduction, which does me much more credit than I deserve, I can assure you. It's a pleasure to be here. It's a pleasure to meet so many new people, so many young people, so many enthusiastic people in a time when, as we all know, doing science is harder than it used to be. So as you know from Kevin's introduction, and as you can see from looking at me, I'm an older guy. So this gives me some prerogatives, and one of those prerogatives is to talk much more frankly than I would have 20, 30 years ago, when you were more worried, or I was more worried, anybody would have been more worried about what people might think of what you said. Well, those days are gone for me. I don't give a damn. Really, what people think, I'm going to tell you what is in my mind and has been for the last 10 or 15 years about vision. And I've enjoyed doing that. I hope you'll get some fun out of what I'm going to tell you about. So as you can see from the title, the question is, or the issue is, how does vision succeed in a hidden world? And that is a strange title, and let me explain what I mean by that in the next 40 minutes or so. And let me begin by this question, which is a really basic one. So how does the visual brain work? And my answer to that is nobody really knows. And that may seem strange to you since, oh gosh, for many decades now, amazingly good work has been done in studying vision as a system in terms of its anatomy, its physiology, its individual neuronal response properties, its biochemistry, you name it, it's been done. And you'd think from all of this information, which would fill a small library, that surely we would know how vision works. And I'm going to tell you why I think we don't know the answer to that question. And the reason is because nobody can explain what it is that we actually see. Seeing, we look out there in the world, I see you, you see me. Seeing is the end product of vision. And until you can explain that end product, what we are actually consciously aware of perceiving, you can't make any claim that you really understand how the system works. And I'm going to try and convince you of that by starting with a very simple demonstration. I'm going to show you a few examples that make the point that what we see is very difficult to explain in terms of the physical world that's actually out there that we all accept. I mean, there are probably some philosophers who worry about esoteric questions like, does the physical world really exist? But that's not the level I'm interested in at all. There's a physical world out there, but we see it in a very odd way that's disconnected from what instruments of physics measure. So let me spend a few minutes talking about this. Why what we see doesn't accord with physical reality. So you've probably all seen something like this. So here are two stimuli. These two gray patches, as you can see from these insets down here, are physically identical. If you take a physical measuring device like a photometer to this one and this one, you get exactly the same reading. They are literally identical from the physical point of view. The amount of light falling on the surface area is the same. But when one is seen in a dark background and the other is seen in a lighter background, they look different. This one looks darker, this one looks lighter. Not tremendously, but they obviously look different. So people have noticed this forever. This is not a new observation. Problem is, how do you explain that? And it's not that people haven't tried. There are lots of explanations out there. But I think they really don't work very well. And let me first of all show you that even though this is a relatively small effect, I mean, this is not really mind-boggling, I think you can make this same phenomenon pretty impressive, and that's the next slide here. So here, I want you to concentrate on the appearance to you of this patch, this patch, this patch, and this patch. And I think you all see it the way I see it, as this being a very light gray, something approaching white, and this patch being a much darker gray, something approaching, or more closely approaching black. And when you take out the information that's in the scene and just leave those patches alone, they are again all physically identical. So believe it or not, photometrically, this area, this area, this area, this area, as you can see, they're the same. So what's going on here? Why should we see this? This is not a trivial effect. I mean, if you can turn, and again, this is not a new observation. People have known since the 1920s that depending on how you present a scene to an observer, the same physical patch can either look black or white. Be made to look black or white. So let me show you another example that is, I think, equally impressive. And the point that this one makes, this, for those of you who may be aficionados, this is called the corn sweet edge effect. And if you look at this, whoops. if you look at this patch, it looks darker than this patch. And not by a tremendous amount, but by certainly an obvious degree. The corn-sweet edge is this little piece of the, you can forget all the stuff around here, it's just artistic folderol. This is the area that's causing this different appearance of these two effects, and you can demonstrate that either by holding up your finger and blocking that little gradient from gray to black or from lighter gray to white, or you can put a mask on it, as I'm doing here, and show that instantly, as soon as you block out that little corn-sweet edge, the two patches look identical, as physically they really are. But when you add back that edge, they look different. That's not a slow effect as you would, for example, experience when you go into or out of a movie theater, take some time to dark adapt or light adapt. This is an instantaneous effect that shows, among other things, that there's no simple explanation for this. I mean, if you go back to this, you might just say, well, maybe there is a straightforward, easy explanation that things that are, as a general rule, surrounded by dark are going to look lighter than things that are surrounded by light. But that's not the case. I mean, there's no surround here. This is something quite different, but the effect is the same. These two patches look different, dark, light, and they're coming from a completely different, very hard to explain source, just this information that you're generating by this corn-sweet edge. Tom Corn-Sweet, incidentally, is now retired, but was a psychophysicist and psychologist in the 1970s who first described this. So let's go a step further and talk about color. So from what I've said so far, you might say, well, okay, black and white, fine. Maybe that's the phenomena that you're talking about are just limited to perception of lightness and darkness. But no, that's not the case. And this is just to show you that they're equally evident in the perception of color. So here, I want you to look at the color impression of this chiclet versus this chiclet, this one being brown, this one being orange. And that's taking, and this is called color contrast. Physically, if you measure this now with a spectrophotometer being a measuring device that's going to tell you what the power and the wavelengths that generate color are of these two chiclets, you'll see that, again, they're identical. The spectrum, the physical spectrum of these two are the same. But you put them in a scene like this, and this one looks very different in color than this one. This is the opposite effect. It's called color constancy, and this is taking two chiclets that are physically different in their spectral properties, putting them in the same scene, and now they look much more similar. These two look more or less orange, even though physically they're quite different. And this is not limited to the properties of vision that we call lightness and darkness and color. You can see this same phenomenology, and if I had time, I'd show you a bunch of other demonstrations of this. You can see it in form, in motion, and any of the basic qualities in vision that we entertain perceptually. In every case, there is a radical disconnection between what's there physically and what you see in your mind's eye, in perception. As I said before, you really have to think twice about feeling any conviction that you understand vision without being able to explain these phenomena, what we see. Why is what we see discrepant, discordant, disconnected from what's there measured by physical instruments? So one way of thinking about this would be to say, and a lot of people have thought this way, one way to sort of rationalize this would be to say, well, these are just illusions. These are scenarios that have been cooked up by me or some other psychologist, and they're exceptions to the rule. But I hope you'll believe me when I say these are not exceptions to the rule at all. These are the way we see the world all the time. Everything that we're seeing, as I look out at you, as you look at me, are being influenced in exactly the same way I've told you. Every color that we see, every lightness, darkness that we see is being modified by our brains, our visual brains, in a way that is discordant, disconnected from physical measurements of the reality that exists beyond our perceptual apparatus. So if you accept that, then the next question is, well, what's the reason for these discrepancies? Why would you imagine, and again, we're not talking about anything terribly complicated here, but why would you imagine that these discrepancies exist? What's the reason for them? And the way I would explain that is by this kind of simple statement saying that our biological sensors can't and aren't in the business of measuring the real world. And what do I mean by that? Well, a way to think about that, that's relatively straightforward for me at least, and that I've used a bunch of times to try and make this point, is to think of a driverless car. So this is a Tesla. I don't know whether it's the latest model, but it's Tesla, I guess it's not doing so well these days. But driverless cars certainly have a future, and we're all going to be using them at some point, whether it's a Tesla or some other brand. And the point of showing you this is that the car, this is just the console inside the Tesla, the cars have the measuring instruments that we don't have. So cars have video cameras, radar detectors, LiDAR, all kind of sensors that physically measure the world in front of the car, behind the car, etc., that enable the car to stay on the road. Those are physical measuring devices that we don't have. Our eyes, our visual system is not like that. We don't have anything that measures lightness in terms of photometric intensity, that measures color in terms of spectrophotometric distributions of wavelengths. We don't have anything that measures distance the way a laser rangefinder measures distance. We just don't have this apparatus. So what the driverless car is using, and using very effectively in machine vision, is very different than what we have. So what problem does that raise? Well, here's the world we live in. Well, the driverless car is living in the same world, but here's a diagram that shows you the problem for us coming from the fact that we don't have the information generated by physical instruments that can actually measure the world for us. So this diagram, our world, the sun shining down on surfaces that have atomic properties that reflect sunlight and absorb the rest of it. And from that light, the reflection is transmitted to our retinas that are sitting out here in our eyeballs, and the information that's coming from the surface that's generated in turn by the illuminant is being distorted in some way by the atmosphere, whether we live in an atmosphere that happily has air in it, and that air, that atmosphere disturbs, changes the light that's reaching our eyes. Bottom line here is, here's the retinal stimulus. Imagine the retinal stimulus coming to our eyeball here. It's a combination of illumination, whatever it might be, the sun or the lights in here, whatever, reflectance properties of objects that light interacts with, and the transmittance of the atmosphere that we are always immersed in. And the retinal stimulus, what comes to our eye, is always an entanglement of these factors, and many others. That this is just a diagram of the simplest categorization of these factors. But all of this information that we get in a retinal stimulus is conflated, meaning that it's just entangled. And how, in God's name, can we imagine disentangling this information so that we can understand what's out there in the world, absent the devices that the driverless car has or that physicists have to measure the world as it really is? So that's the problem, and I'm going to spend the rest of the time talking about how that problem might be solved. And let me begin by showing you how it's pretty clearly not being solved. It goes back to the 1960s and 70s and 80s and the work of a large number of people, but I think the seminal people in this lineage were David Hubel and Torsten Wiesel, who in the late 1950s, 60s, on through the 70s and 80s worked together over 25 years to first establish the characteristics of neurons in the visual system of experimental animals. And they started working on the cat, and this diagram obviously is a cat. And the way in which they approached this was to put a microelectrode into the visual region of the cat's brain. The cat was anesthetized, but the visual system was still working perfectly well, or at least well enough to do these kinds of experiments. And the animal was sitting in front of a tangent screen, and on that tangent screen were shown various stimuli. You've probably all seen videos of this. There exist on the internet, actually, a very nice video of the two of them doing an experiment. So the kind of work that they did was to present on the screen, just as an example, bars of light that were in different orientations: horizontal, vertical, back to horizontal, and oblique orientations in between. And what they found, and again, this is just an exemplar from one of the many, many experiments they did with all kinds of stimulus characteristics, but the answer is pretty much the same for whatever they tried. What they showed was that a neuron, imagine recording from an individual neuron in the cat's visual cortex, neurons responded to the features, the feature in this case being orientation, in a very dramatic way. In some orientations, again, this is just an example of one pretend neuron, but this is actually what they saw. A particular neuron could, for example, respond to a horizontal stimulus with no action potentials at all. Each one of these tick marks is an action potential showing the vigor of the neuron's response to the stimulus. And as you see here, as the orientation of the bar became more oblique and closer to vertical, the cell would respond more and more vigorously, and then again, as you went back to horizontal, the response would deteriorate and disappear altogether. So you could generate a curve, a tuning curve for a neuron. And again, I emphasize that this is just one kind of stimulus that was used in their 25 years of experiments on this time, over this time, first in cats, then in monkeys, and it's absolutely seminal work in neuroscience. I mean, I think it shaped thinking about systems neurobiology more than any other experimental body of evidence that persists today from this really enormously influential work. What's the idea that's come out of this? The idea that seems obvious here is that, well, neurons are responding to features in the world, whether those features are the orientation of the stimulus, its lightness, its color, its movement, its direction of movement, you name it. The cells are going to respond to features of stimuli that are presented on the retina coming from stuff in the real world. But from what I've told you, this, what I would call the standard concept of feature detection, won't work. Why? Because you're not seeing the physical reality in your perception of this that exists in the world. So take, for example, an oriented bar. Think of a rod, and think of the rod being held out in space instead of a bar on the tangent screen. Think of a bar, let's say, 10 centimeters in length. Well, if you hold the bar in a frontal plane, it'll look something like 10 centimeters in length. But if you hold it coming away from you, going away from you, or coming towards you, perception on your retina is of a shorter bar. Obviously, that's just projective geometry. I mean, that's grade school stuff. So the orientation that the cat neuron indicates is the response to an oriented stimulus can't really tell you what the orientation of the rod in the real world is. And you can go through the same argument for lightness or motion, direction of motion, form, what have you. So again, I just show you this as an example of feature detection, but it is just one of many experiments that they did that make the same point. It seems, and everybody certainly I did when I took a course at Harvard from these guys, and wow, man, it's really impressive. This must be the way vision is working. The neurons are responding to the orientation or to the qualities of physical stuff in the world. What more needs to be said? Well, it just can't work that way, and the reason it can't work that way is because of the demonstrations I showed you before. So what would be the way in which you could think of a solution to this problem? So the question, and it's the title of the talk that I showed you when you came in, the question here is, how can we behave successfully in a world if we can't measure it? The world physically is cut off from us because we don't have the instruments that the driverless cars or any machine vision apparatus has. Well, obviously we behave as if we knew all that information, but we're not getting it physically as feature detection would suggest. It's just not possible. This is not a criticism of people in Weasel. They were very smart guys. They weren't trying to make an argument about perception. They were just trying to say, how do neurons respond to stimuli? And they did a wonderful job of that. And in 1981, won a well-deserved Nobel Prize. So the answer to this question, as far as I'm concerned, is that no one really knows how this question can be answered. But what I'm going to tell you in the remaining minutes of the talk is a way to think about this puzzle. What would be a way to think about how the visual system is working if the simple idea of detecting features that correspond to the physical reality in the world is a non-starter for the reasons that I've said? So let's go back and think about this example I showed you before and ask the question that I've put up here. Is this discrepancy explained empirically? And that is to say, is this phenomenon, is seeing this lighter than this in different surrounds when they're physically the same, is that a product of trial and error experience rather than measuring features of the world that we have no mechanical, physical way of measuring? We just don't have that Tesla apparatus in our visual systems. And if you wanted to look at that problem and ask, could you explain the difference between the appearance of this and this being lighter in a dark surround and this being darker in a light surround when they're physically exactly the same? Could you approach that? Could you explain it by the experience that we as human beings have always had? And I don't mean by that we as individuals living our little lives over whatever the decades we have to live them, but I mean the experience of the species over the millions of years that Homo sapiens evolved from much different predecessors. So if you want to make a case that that is what's happening, that it's the accumulation by trial and error of the experience that we've always had as species over evolutionary time or individuals over lifetimes, you would have to collect a body of information that indicated, for this example, for instance, what was our experience? What really is the experience we've had when we've seen two patches like this that are the same in a dark surround and a light surround? Could that accumulated experience, by trial and error, rationalize, explain the phenomenon that we see here, and indeed the other phenomena that I've shown you and others that I haven't. So it's not impossible. I mean, you say, well, you know, I guess you'd be skeptical at first. I mean, you'd say, well, look, it's really not going to be easy to understand what human beings have always seen. That just kind of beyond the pale. How are we going to do that? But if you think about it a little bit, you say, well, it's feasible, it's possible. So what you do is you take a large number of natural scenes in black and white, and there are databases out there that contain thousands of pictures like this that you can analyze and that we did analyze, and ask, is this human experience able to explain the phenomenology of the simultaneous contrast effect, those squares, that's the official name of it, simultaneous lightness contrast. Can you explain that phenomenology on the basis of empirical information, what we have always seen in our lifetimes and what our species has always seen over evolutionary time? So you take a bunch of pictures like this, a very large bunch of pictures, and you analyze them by the following way. So here's our little problem: dark surround, light surround, making, for some reason that we puzzled by, making this one look lighter and this one look darker when they're physically the same. So here's what we've been talking about. Here's just an example of the sampling of a natural scene, or a piece of a natural scene. So you put the template for these projections onto the retina into natural scenes, not once, but literally millions of times, not hard to do with computer technology, and you ask, when the surround has been dark, as in this case, what is the luminance, what is the light intensity of the center of the little template? And conversely, you can ask, when the surround has been light, and you ask the same question, what is the typical empirical luminance of the center square when the surround is light? And as I say, if you do this millions of times, you can come up with the answer to that. So here's the answer in terms of the frequency of occurrence of the center square, the luminance in the center square when the surround has been dark versus when the surround has been light. And here are the two results. These are very smooth curves, but this is actual experimental information. The reason they're so smooth is that the database is huge, so, you know, curves look phony, but they're quite real. So here, this is the light intensity on the x-axis, and this is the probability of its occurrence. So here, you see that the probability of occurrence of the luminance in the center of a dark surround is described by this red curve, and that it is shifted to the left with response to the light intensity described by the blue curve, i.e. the collection of empirical information when the surround is light. So this is just, you know, nothing really terribly complicated about this. You've just taken a whole bunch of pictures. You've asked, what is the typical luminance, light intensity, that has existed in the center of a template with a dark surround versus a template with a light surround. And they're different. These two probability distributions are obviously different. This one showing that the intensity here tends to be relatively low compared to the intensity here. That's the empirical information. That's what we've always seen as human beings living in the world on Earth. And here is the ranking of the information in these graphs plotted as cumulative distributions. So this is just the data of this very red curve plotted differently as a cumulative distribution going from 0 to 100 or 0 to 1. And this, the distribution for this curve going from, again, from 0 to 100 or 0 to 1. So what's the meaning of that? Well, if the answer to the question is yes, the reason you see this phenomenon is because our experience has told us that we're going to succeed better in the world when we see a lighter surround in a lighter center in a dark surround and a darker center in a light surround. That experience has told us that we're going to do better in evolutionary terms or in survival terms in our lifetimes if we see the world that way. That's all this means. And here what you see is that let's say that this is the target intensity. So here's now the intensity in the center, and these are now both the same. The rank of this intensity, again, same intensity, call it X. The rank of intensity X here is much higher than the rank of intensity here, even though these two patches are the same. So if our reasoning is that the reason we see this phenomenon, this lightness contrast, and again, this applies to all of the examples I showed you before, the reason we see this is because we're not judging this on the basis of measuring physical reality. We're judging it on the basis of our experience over millions of years as a species, over tens of years as individuals. This is what we get. The prediction is that you're going to see, because of this empirical experience, you're going to see this one as lighter and this one as darker depending on the surround. So that's the argument. And I think it's a perfectly reasonable argument. And as I say, this is an example that I hope is simple enough so that you can understand. I mean, I could go through the same kind of reasoning with color, with much more complex examples of light and dark, with orientation, with movement, with direction of movement, and so on. Suffice it to say that it really turns out to be one size fits all. If you get the empirical information about what we as human beings have always experienced, you can explain, you can explain this. I was pressing the wrong button here. You can explain this and a whole bunch of other phenomena that are equally puzzling, some of which I've shown you, the corn-sweet edge, the more intense light-dark stimulus, color, etc., contrast and constancy. All of these fit under the umbrella of empirical information generating what we end up seeing, what we end up perceiving. And the question next is, well, why does this strategy work? Why should that work? And the answer is, at least the answer I would give is, that because it's not tracking physical reality, it's tracking behavioral success. And behavioral success in terms of Darwinian survival in a complicated world is not physical reality, it's something quite different. And I'm going to spend the last couple of minutes trying to indicate to you why that's really inevitable when you think about vision or any other sensory modality, why it's inevitable in thinking about how the system must work, why it's impossible to see things for what they really are physically. We don't have the apparatus. Why do we see things empirically and predict them on that basis? It's because that tracks behavioral responses and behavioral responses. And the success of those responses are what it's all about. So let's think of the problem in a somewhat different way. So this is the game of Go. I'm sure a lot of you have played Go or at least seen the Go board. And this comes from a long line of thinking and working in computer science in which people have tried to beat human beings, and you're well aware of this kind of effort over the last few decades, either at checkers or chess or the most complicated board game that exists that we play today, and this is widely played in Asia, the game of Go. What's the problem in checkers, chess, or Go that has made it, first of all, possible for Deep Blue to beat Garry Kasparov in 1996 or whenever it was at chess? That was a brute force computer approach that was basically a combination of trial and error mixed with playing a lot of known chess games and shortcutting in those known games strategic moves that would be winners. So that worked, and Kasparov, the reigning world chess champion at that time, was beaten by Big Blue, the computer program that challenged him and won. So what's different about the game of Go? Because this is now in the last 5 or 6 years that this has evolved as the next computer science challenge. Okay, can a computer system beat a human being? It happened to be a Korean named Lee Sedol who was, in fact, beaten by a computer system playing Go a few years ago. What's the difference between chess and Go, and how is this pertinent to what I'm talking about today? The reason is that the problem space, the solution space in chess is enormous, but it's not as enormous as the problem space in Go. The number of possible solutions to the move you should make for a given board position to win at Go. The problem space for Go is about 10 to the 170th power. Can anybody imagine a number that big? I mean, it exceeds by far all the atoms in the universe. It's just too big to ever think about in terms of a rational, algorithmic, logical solution that our brains could have evolved to play the game that's even harder than Go or chess, which we might call the game of life. The responses that we make to allow us to succeed in the world in terms of, again, evolution or individual lives is vastly greater than a board game like Go. The number of possible moves and their advantage or disadvantage to the player is just impossible to conceive in an algorithmic, logical way. You can't do it. So how did the computer beat Lee Sedol, the world champion, the world Go champion? Well, the answer was it did it empirically. It did it by trial and error, by having machines play each other millions of times and encode the right move, not in a specific way, but the right move that would likely be advantageous, not on the basis of any detailed logic, impossible, but on the basis of trial and error. What worked, what didn't work. And that's a very different approach than the approach that was taken in checkers many years ago, in chess, Go. And this is a program, incidentally, for those of you who are interested, this is work that was done by David Silver and his team at Google. And it's amazing that they succeeded in doing this, but in another sense, it's not amazing. It's what, in my view, the visual system or any other sensory system is doing. The game of life is just too damn complicated to work out success in terms of any framework except an empirical framework. Try it. If it works, change the circuitry of the visual system or the computer system. Change it on that basis, empirically, what worked, what didn't work, and damn the torpedoes. I mean, that's, I think, what basically was done here. Well, what does that imply about the way the visual system, the visual brain, is really put together. What is it doing? If it's not doing some kind of algorithm, some kind of logical procedure that lets us know what the right move is to any visual stimulus, to anything we have to deal with in the course of our existence, what's the brain structured like? I mean, how are we to understand the Hubel-Weasel complexity of the nervous system that, is out there as a challenge for today's neuroscientists? And this may seem a joke, and in part it is a joke, but I mean it at least half seriously. This is a Rube Goldberg machine. I mean, if you look on the internet, Rube Goldberg was a cartoonist in the 20th century, in the 1920s and 30s. He was a sports writer for the San Francisco Chronicle, I think. And he started doing cartoons that were just crazy cartoons of how you could solve problems empirically that, were just off scale and made people laugh. Well, this is a Rube Goldberg setup, and if you've looked at this, or if you look at this particular one, or looked at any of these Rube Goldberg machines, you see that there's no logic to them. It's just structure put together to make something happen empirically. Stuff happens causally as a causal change in this apparatus that makes no sense from a logical point of view, but makes perfect sense in terms of thinking about what I've been talking about. So, like I say, this is part a joke. I mean, I don't mean this to say that the brain is literally a Rube Goldberg machine, but I make it only partly a joke because I want you to think about the possibility that it could be at least along these lines. That is, no algorithm, no computation, just circuitry that's been encoded. I use the word encode loosely. That's just been encoded by trial and error over millions and millions of years of our experience as human beings and of the predecessors of Homo sapiens. So let me draw things to a close here and just reiterate the key points. And if you remember nothing else from what I've said, the main point I've tried to make is that vision can't measure the physical world. We just don't have the apparatus to do that. And the goal of visual systems, in some sense, must be to overcome this obstacle, which is a very basic one. And the argument I've made is they do so by generating percepts on the basis of behavioral success, not on the basis of measuring physical reality. And that what we end up seeing is the empirical rank of the frequency of occurrence of stimuli, empirically processed, not logically processed. And the bottom line, in one sense, is that vision may be a lot simpler than we have imagined. So I was at a seminar a couple of days ago at Duke, and it was a seminar debating two models of how the retina might work. Well, the retina, as you know, is just the input part of the visual system. And the model was so damn complicated with so many free parameters that, it was mind-boggling. I mean, you could imagine sorting out in an algorithmic, logical way what computation is being carried out by the retina, but you could also say, you're never going to get from here to there because that's not what it's doing. It's not making a logical computation of the stuff that's on the retina to tell you about the physical world. It's doing something quite different. So the implication of that, of course, would be that if the visual brain works in that way, that says something about how the brain in toto might be working. And I'll just end by saying, if you want to find out more about this, you can go to my website. You can read, if you're so inclined, any of these tedious books. And that's it. I'll be glad to answer any questions you have, and I'm sure there are plenty of them. So fire away.
Say one thing, that there's a reception to meet and greet Dr. Purves out here
Liz. By the way, I said I was an old man, and one feature of being an old man is that you're a little hard of hearing, and so speak up.
So what you're talking about is making me think of sparse coding, and isn't it possible that some of this is an artifact of the brain, of our need to sort of streamline the amount of information that's going in, and it's getting mixed up?
I think that's a perfectly legitimate argument. So what Liz is referring to, sparse coding, which has been around since, 30 years or so, is the idea that the input to the visual system is far too much for the system to handle. And as a result, you have to discard a lot of information by filtering and select the information that's biologically useful for the purposes of efficiently passing on to the central nervous system the information that's going to allow us to see whatever we see. I really don't have anything against sparse coding, but I don't see that as the solution to the problem. I mean, I think that's all perfectly reasonable, and certainly what seems to be happening as you go from retina to thalamus to visual cortex and beyond. But I don't think it can answer the questions or address the questions I'm raising here. But sparse coding is out there. I don't have anything against it.
What would be the survival value of the two examples you made of the light and dark and the blue and red?
So that's a very good question. What's the survival value of seeing things in this way? I would say the survival value is just that this is the way that vision evolved because of the problem that I said. It couldn't solve it by seeing the world based on physical reality. It had to do something that was radically different. I've suggested what that radical difference is, but we wouldn't be here to talk about it if it hadn't worked. And it works, the argument I made is that it works because it tracks behavioral success. That's very different than tracking reality. So what's the specific advantage of seeing the little templates of light and dark? None. That's just the signature of the way the system evolved. There's no specific advantage of seeing things in that way other than the advantage that it worked. So that's, a tricky answer and maybe kind of a philosophically oriented answer, but that's what I believe.
When you're talking about evolutionary advantage, especially in the visual system, what about the fact that in the last 100 years, lighting has changed? We didn't have fluorescent lighting 100 years ago. We didn't have white lighting and cool lighting and more lighting 100 years ago. So how would that apply to what we see today? Because that takes longer than 100 years ago.
Well, that's another good question. So I think if I can rephrase it a little bit, is how does the fact that is that something I'm doing? If I could rephrase it a little bit, it would be the world has changed, obviously, over modern cultural existence and what was true hundreds of thousands of years ago. And the only way I can answer that question would be to say that if we were talking about life on Mars that had evolved in a different system with different lighting and different experience, of course our visual systems would be different. What the effect of fluorescent lights over the last, whatever it's been, 100 years, et cetera, I would say that's probably not making much of a difference. That's probably not making much of a difference, but I think it's worth thinking about. So we're soon going to discover life someplace else in the universe. I hope on Mars, and I hope that you and I will live to see that. But if we don't, it'll be discovered at some point. And my guess is that, yes, the visual system of us, if we'd evolved on Mars, for example, would be different depending on the experience that we had. It's not going to be exactly the same. Yeah.
you're saying about feature extraction. Something I grew up with, but,
Yeah, so did I.
so what about areas of specific lesions in the brain can cause the loss of specific features? Is that because we're losing a perception of stimuli, a percept, as you say, or are there not areas of the brain that are really dedicated to assembling features?
Yeah, so the question, I don't know whether you all could hear it, is what about features known to exist in different brain regions that are pertinent to what you see? So the two that people usually bring up as examples of that are the region that's responsible for color, the V4 or V5? Huh?
V4.
V4. And MT, which is a region responsible for motion. That if you record from those regions, you got a lot of neurons responsive to color, a lot of neurons responsive to motion. And if you have suffered damage, either experimentally, I don't mean us, but experimental animal has been damaged in those regions, or human by stroke or accident, yeah, you lose a lot of color vision, or you lose allegedly the ability to see motion normally. So I don't know what that means. I mean, I think the visual cortex is pretty much a black box outside of V1, and I have no idea. You know, as you know, there are many debates about how restrictive those areas really are dedicated to those functions, how restrictively they're dedicated to those functions. But I just say that at the moment is beyond what we know enough about to say. If I'm more or less right, you wouldn't expect any great allocation of specificity in the brain in the style of V4 or MT, but the jury's out. I don't know.
I've also thought of it as a, survival mechanism. Also, it's just the brain over-interpreting. We're so good at picking up motion and contrast, and the brain is so good at finding these patterns as it goes from the visual cortex around the brain that it's the brain over-interpreting in these different contexts.
I don't know what to say to that question, but it doesn't kind of ring a bell with me, because I'm not sure what over-interpretation.
In certain contexts, maybe this.
Yeah, I mean,
survival.
Everything depends on context. All of these, everything that we see, everything that we hear, everything that we smell, etc.
Just the brain is so adept at finding these patterns and interpreting them.
It's absolutely dependent on context. And to me, that kind of fits with the argument I'm making, that it's not a simple, the luminance at a spot or the wavelength at a spot on the retina that's causing what we see. It's the whole gamish, the context and the spot. So, but how to answer your question in those terms, again,
just that the brain is so good at finding these patterns.
It's very good at it.
And then it's too good sometimes.
It's very good at it, but saying that it's too good at it, I don't know. We're very, very good at it, no question.
Context.
Saying that we're too good at it, I don't know. I don't know what that
Trying
means.
to find those patterns.
Yeah. So, again, I'm not the source of all wisdom here. Who else has got a question? Kevin.
In regards to boxes, our brain wired so that we want to see the different contrasts, right? Yeah, so in regards to those boxes that you showed, I mean, our brain, we're wired, in terms of the visual acuity, we want, it's easier to process, contrast of black versus dark. So I guess, can you comment on that? Is that the behavioral situation where our brain likes to just go that way as opposed to?
So Kevin, I think is raising the question, but maybe rephrase it if not. What's the significance of contrast? Why is it that we are particularly attentive to dark versus light. And one answer to that, and as the brain evolved to specialize in that, and a lot of people, of course, have said yes, that the reason that we like contrast is that in the experience that we've all had, light versus dark contrast is the way we see edges, or differences more broadly. I mean, if you look around the room, you'll see lots of contrasts that are edges, lots of contrasts that are not edges, but are distinct entities in the room. And of course, we want to see those things and respond to them correctly, but I don't think, I mean, I think that it's not against, it's not particularly for what I'm arguing for, but it's not against it either. I mean, I don't think there's anything evolving to see little boxes is not what it's all about. Little boxes are just a way of simplifying stimuli for the purposes of this or any other kind of argument about contrast in vision, but I don't think that it weighs in one way or the other. It would be my sort of first reaction to your question.
It seems like wouldn't a lot of these changes, what you're arguing for, wouldn't it have to be encoded genetically somehow? Like, would you expect if you could find some sort of ancient human DNA from, let's say, 50,000 years ago or 100,000 years ago, that you would be able to detect, should you be able to detect some sort of genetic code differences between then versus now to go along with your idea of this empirical over time changes to make our modern visual system?
Yeah, so the question about genetic explanations of this or anything else, I think cut both ways. So I think we would all agree that all of the properties of our physiology and anatomy have some genetic explanation, including all of this. So, I mean, this is not any different than explaining why we have, 3 cone types in the human retina versus different numbers in other animals, et cetera. It's got a genetic basis among other epigenetic bases. But I don't think that's really going to be the answer to anything. I mean, I think people who've looked for specific genes, as you know very well, I mean, people who look for specific genes as the cause of X, Y, or Z, a behavior, a disease, have generally been disappointed that, there are many genes involved, and it's a hard go to say what the important ones are, whether it's autism or schizophrenia or whatever you're interested in. And I think that the same would be true here. I mean, I doubt that there are any specific genes to this, but of course, all of this has a genetic basis like everything else. I don't know, maybe that's a non-answer to your question, but best I can do. Okay, we done? Thank you. Oh, one more.
Does handedness have to do anything with vision orientation, like left-handedness versus right-handedness in real life? Or is it the other way around? Does vision influence the handedness?
The question is, does this have anything to do with right or left-handedness? So, that's another kind of mystery that actually 20 years ago we wasted a lot of time studying right and left-handedness in the somatic sensory cortex. But I don't see any obvious connection between the two. I mean, there might be, but nothing jumps to mind. Okay, thank you all very much.